Okay, let's get started with this practice Hess's law problem. So I cut and glance at all three of my steps here and tried to decide where do I want to begin. I think I like the idea of beginning with this step. So the first step here. Why that is because I have this BCl3. I know it's supposed to be located over here on the product side. Since it needs to be on the product side, I'm going to have to do what to this particular step? Yes, flip, and I'm glad somebody pointed that out. This has a 2 in front of it, so we're going to have to multiply this one by 2. That is correct. So it only has a 1 here, over here in the step, so we need to not only flip it, but multiply it by 2. So we're going to do that. Going to go ahead and start there with the 2H3BO3. That's like boric acid. And I'm going to go with 6 hydrogen chloride. And then we get our 2 boron trichlorides and our 6 waters. Now over here to my delta H, I need to change the sign so it's going to become positive. And then I multiply the 112.5 by 2. And that should give me 225. So here I have a positive 225 kilojoules. So that's the first step. Now I did kind of scan around and see that 2 of my series here has the hydrogen chloride in it. So what I'm going to try to do is not focus on that, and hopefully it's going to end up working itself out by looking at other things. So I look at the second series of our reactions here. I have the B2H6 here, the B2H6. And I noticed that that's also here on this side, and it's the same 1 mole relationship there. So do I need to do anything to this second step? I would say no, exactly right. So I'm just going to rewrite it down here for cancellation purposes. And it's good to always make sure that everything's going to cancel appropriately, and that's how you would need to show your work. Now, whether you need to rewrite it or not, the ones that you have to flip are kind of hard not to rewrite them. But so I'm just going to leave this one the same over here. It's going to be negative 493.4 kilojoules. All right. And actually, this should be a 0.0 because there we go. All right. Now, looking at the last step here. I have hydrogen, chlorine. Chlorine's up here in the overall. So it's in the correct side. It's on the reactant side, but what do I need to do to this whole thing? Yes, it's going to have to be multiplied by 12 because this is 1/2 of the chlorine, so I need 6. So I'm going to multiply these by 12. So I get 6H2 plus 6Cl2 gives me 12 hydrogen chlorides. My delta H then becomes, I'm not flipping it, so I just multiply by 12. 92.3 times 12 is negative 1107.6 kilojoules. So before I even add them up, I want to make sure and cancel everything out. That's the next or last step I would engage in. So I go here, H3BO3, not up in my original equation, so it's got to cancel, and guess what? It does. Check. 6HCl, well, that one's up here, but it's over here, so this one cancels, and this one turns into a 6. So the 12 canceled. Sorry, that got all messed up. This was a 12. It cancels to a 6. Check. And that's good because that's in the right place. Now let's keep going. Looking at this one, the BCl. that one's good. This one is supposed to be in our equation, that one's fine. The 6 waters, those cancel right here on either side. The B2H6, that one's up there, good. H2, those are going to cancel. This one's up here, good. Now that I see that I have all of the correct things in their correct places, I can just go over here and add the 225 plus these two negative numbers. And you should end up getting negative 1376.0 kilojoules. And that's going to be your delta H of the reaction for our overall one right here. So good Hess's law practice here. Reviewing that, that is definitely a problem that you'll either see in the free response or the multiple choice. Hess's law is definitely one I see pretty much through all of the practice tests and stuff every year. Now, learning targets for today. And today we're probably going to get through solutions and reactions. We're going to get through some of this today, explaining exchanges of energy, different systems. And the systems is it a solution, creating a solution that would be dissolution or dissociation process? Is it combustion? Is it reaction? Is it formation? These are the different systems we're talking about. So formation, combustion, solution, and reaction is more of a general term. And these other three are a little bit more specific. We're probably not going to get to the bond energy stuff today, but we will, visit that next class. And we'll look at the bonds broken from the reactants and the bonds forming and how we can calculate delta H using that equation. And we'll use the dot structures to figure that those different bond energies out for the bond enthalpy. But we are going to analyze and interpret energy diagrams today. So we will be definitely taking care of that one as well. Just a quick review from our last set of notes talking about the system and the surroundings. Remember, the system is always like the chemicals that we're looking at. So this is going to be your chemicals. The chemistry part. What's interacting? Is it solution forming? Is it reaction? Is it combustion? The chemicals involved, that's always going to be the system. The surroundings, everything else around those chemicals. And also, for later purposes, do remember that anytime you're recording a temperature, temperatures are taken by devices that are located in the surrounding. So any kind of temperature values that you see are always measured from that perspective of being in the surroundings. So if the temperature increases, the surroundings is getting warmer. And if the temperature decreases, that means the surroundings are getting colder. So therefore, you have to, decide on what's happening with the energy flow based off of that. We'll be revisiting more of the temperature stuff, especially when we get to calorimetry, because then we'll be using temperature changes to figure out heat flow. Now, endothermic versus exothermic. Remember, endothermic is the heat flow into the system. It is when the system absorbs energy from the surroundings. So keep in mind, we'll be looking at the different situations of endo versus exo. And opposite, of course, exo is when the energy leaves the system. It's going to the surroundings. The surroundings is gaining the energy, or you could say being released to the surroundings. Lots of different ways to state it. However, the more important part of endo and exothermic, following the law of conservation of energy, which is the first law of thermodynamics. So it's not created nor destroyed. Energy just gets altered. So when we talk about the system gaining energy from the surroundings, the energy lost from the surrounding that's gained by the system is the same amount. It has the same magnitude or value. They are just different directions, and the different directions are denoted by the signs. So system gaining it is positive, the system loses it, it's negative. It's just the direction, but that magnitude or that value of the measurable heat, that is going to be the same. Reviewing what enthalpy is, again, it's a state function, so we're really concerning ourselves with the final and initial states. And by definition, as it works out through all those derived equations, the delta H is going to be equal to the heat, which is Q, at constant pressure. So we're talking state function. We don't really care about the pathways here. This is like the final state minusing the initial state, because of course the products would be the final and the initial would be the reactants if we're talking about a reaction, and therefore falls under that particular realm of, umbrella of idea. Now this is the basic, setup of the state function. We're going to be using a more specific equation later on that's on your formula sheet, but it's the same idea. The heat that's within the bonds of the products minusing the heat, the heat that's within the reactants, that gives you your change in the heat, and then you, by the sign, you know which way the heat's flowing. So delta H of reaction describes the energy change for a reaction. And if the delta H ends up with a negative sign after all you're calculating, that means it's exothermic. The positive sign means it's endothermic. Once again, that sign designation is basically referenced off the system here. So if the system's gaining, then it's absorbing, then it's positive. If the system's losing, then the delta H would be negative, because then it's being released to the surroundings. There's going to be ways of finding delta H with calculations. There's also a way of telling based off of like the energy diagrams, which is what we're going to look at now, and be able to see this is, why these actually come out the way that they do. Now here is our lovely energy diagram, and yes, some of this stuff is a little faded, so I'm going to go ahead and highlight that for you so you can label your graphs appropriately. Here is our Y. And always on the Y is going to be the energy. Now that may not say potential energy, but it'll have some kind of energy measurement over here on this side. In this case, kilojoules. Sometimes it could be kilocalories or calories. It might be some other kind of heat amount, some kind of heat unit or energy unit. Down here on the X, it's going to be the progress of the reaction. Or sometimes you might just see it written as time and it has an arrow pointing that way. So the progression of the reaction, as time goes on, this is what's happening. Then we have designated here a line for reactants and a line for products off of our chart, and sometimes these will have numerical value to them, so you'll be able to actually interpret and decide the numbers. So this first line over here to the left is always going to be designated as the reactants. This is the potential energy in the bonds of the reactants. Over here, this lower line to the right, the one that's over to the right is always going to be what the energy is stored in the products, in the bonds of the products. So this difference right here between the two is how we would calculate the delta H off of this particular diagram. Now, if delta H, of course, is H products minus H reactants, if the product amount is lower and the reactant amount is higher, that's why this is going to come out being negative. And you're going to have a negative delta H there. Couple other features on the graph that aren't as important as of right now happen to be the transition state up here, which is the top of the hill. Okay, this top of the hill, this dotted line that's the energy of the transition state. And here the activation energy goes from the reactant line to the top of the hill. This is called the EA, or the activation energy. That is the amount of energy needed to get the reaction started. These two features, the activation energy and the transition state, those are going to be talked about in detail when we get to kinetics, because that has to do with the speed of how fast the chemical reaction occurs. You do have energy changes going on in here, don't get me wrong, because you have bonds breaking, bonds forming, and lots of intermediates that are unstable, so that's why this is a very high energy area of the diagram. But for our purposes and for delta H, we really, once again, state function, we care about, you know, final, this is final state, we care about initial state. Those are the two things there that we're going to be, you know, paying attention to right now. So this would be the general look of the exothermic, okay, where delta H is negative. Energy is being released from the system to the surroundings. General idea there, as you see on the diagram. Now the endothermic graph is similar. It has a couple different features though that we'll talk about now, and you can label. Anybody find one of the most noticeable differences between the two? Would like to note a notable difference? Yes, the reactants and the products lines are flipped in terms of their amounts. The reactants down here start at a lower amount of energy, whereas the products on the right here are having a higher amount of energy. That's true as we dot along here, and that is why, good point too, we're going to get to that as well. So our change in enthalpy of H products minus H reactants, this is why this ends up becoming a positive delta H here, because our product line is higher. So we're going to get a positive amount here for this measurement. As noted, just stated, this activation energy hill is much higher, yes. Endothermic takes a whole lot more in order to get to the amount needed to start the bond breaking part of, which is the initial, have to break the bonds first before you can form new bonds, and get up here to this transition state. To do that takes a lot more energy usually in endothermic, but it has to absorb energy in order to end up getting started. So that's the general idea there. Let's look at an example problem. Some of these problems that you'll see, they actually give you a graph and they start the reactant line for you, and you have to finish the hill and position the products correctly. So if it's exothermic, you would make sure your product line would be lower than the reactants. And if it was endothermic, you would position and make sure your product line would be higher than the reactants. So sometimes they actually make you draw it in like a free response question. Or they can give you something like this where they give you a multiple choice version to follow. And our multiple choice here showing we have a generic reaction of A plus B giving you C plus D. So A plus B and C plus D on our overall graph. So before I even read the question and I look at this graph, what can I automatically and easily tell? Yes, that this is exothermic. I can tell that because here's my products and it's lower than my reactants. They also gave me numerical values so I can find the difference between the two. So that's going to be 20 kilojoules right there. All right, so basically, which of the following best describes the flow of heat for the reaction? Well, the heat is going to be the final minus the initial state. So obviously these other ones must be wrong because we already determined that it's 20 kilojoules as the difference there. If you want to see like the 60 they put in here, That's because that's actually the activation energy. And then the 100, of course, comes from being the transition state. So those would be eliminated because they aren't actually looking for the amount of heat for our reaction, our delta H. We've already decided that it's exo. And what we're looking for here is that since it's exo, we have two choices. The 20 kilojoules of the heat is transferred to the surroundings, or the 20 kilojoules of heat is transferred from. So to or from, which one should it be then? That should be A. That is correct. This would be the correct answer. Now the question was posed once again, what is the transition state right here? This is the top of the hill. That is the amount of energy involved when the bonds are breaking and forming and you have intermediate compounds in between. That's more of a pathway thing. So we're going to talk about what's going on inside the hill when we get to kinetics. So we'll be referring to more of this. For our purposes and for this unit, really you're only looking at products minus reactants here, final state minus initial state, giving you your change in the heat. That's all we really care about for this particular set of concepts. Now, types of heats of reaction. I guess the most basic one we can talk about is formation, and of course they designate it with a little F here. What is the heat of formation? The heat of formation is the enthalpy change for the formation of 1 mole of the substance or compound. This could be this is going to form some sort of compound. Now, formation, of course, is saying that it's being formed from its elements. So it's being formed from the elements that are in the compound. Not formed from the elements. So you might want to make that designation as well. We're making 1 mole of the substance, and this is why we start seeing these fractional coefficients, because if we're representing 1 mole of the substance, and stuff from certain elemental forms isn't going to allow you to balance it that way without using fractional coefficients. And let's take a look at an example like that. So what would the reaction look like if describing the formation of water? Well, the formation of water, H2O here, we're forming water. Kind of drew my O a little far away there. And since by definition it's forming 1 mole of the water, what are our two elements in water? That would be forming H and O. And yes, exactly right. I see some of you pointing out to me that hydrogen and oxygen in their elemental form are going to be diatomic. So we would write them over here as diatomics. Okay, like so. Now, if I'm following the formation idea correctly, I have to balance it so that it's forming 1 mole. And if I'm doing that, my hydrogen's okay because I have 2 hydrogens, I have 2 hydrogens. That part's already balanced. But look, I only have the 1 oxygen over here. So what does that mean about the coefficient here? Yes, it's going to be a half. It's going to have to be a half. Exactly right. And this is how I would write out the formation of water from its elements. Like so. Synthesis of 1 mole from its elemental components. Very, very important there. Now let's go ahead and have you try writing out a formation equation for a different compound. Let's look at methanol. So go ahead, take a moment, try to write that out and balance it appropriately for the formation of methanol. Okie dokie. Now I always start by, when looking at these, thinking about my product over here. So that's what I'm going to do, is write out my product over here. Like so. Then I can work backwards to adding in all of my elements. Now you can start with just looking at the elements and start writing them out over here. Remembering, of course, that I'm going to balance it with 1 mole. So what's my first element to put over there? Carbon. Now, is carbon diatomic? No. Okay, so we just write C. And if you know anything about carbon, you would know that it's a solid at normal room temperature, so we would be citing those kind of phases. So there aren't many nonmetal solids: carbon, phosphorus, sulfur, selenium, and iodine, I believe, are the only ones that are actually elementally solids at room temperature. The metals are bromine and mercury are liquids, and then everybody else like hydrogen, oxygen, all of those are going to be gases. So let's go ahead and we can write them in as gases because we know elementally they would do that. Not necessarily, but you know, for what you might see them written anywhere, either on the internet or in your textbook, they usually will have their phases next to them. Unless I designate it to you or it's, you know, shown in the problem that way, I wouldn't concern yourself too much with it. Yeah, methanol actually is a liquid. It definitely is. Ethanol, the alcohols, they're all alcohols. They're going to be liquids at normal conditions. This is true. Let's get on to balancing this guy, though. How about the carbon? Do we need to do anything with the carbon? No, you don't have to. And no, it does not matter which order you put the reactants in. That's a good question. It does not matter. I just start with the first one in the compound. That's why I did it that way. All right, so carbon's fine, 1 to 1. How about hydrogen? Hydrogen needs a 2, very good, because there's 4 over here. Now, how about the oxygen? It is a 1/2 here. Exactly right. Good, good, good. Now let's look at molar enthalpy of combustion. Notice they changed the little subscript here. So now we're referring to combustion reactions, not formation, combustion. Molar enthalpy of combustion for the compound describes the enthalpy change occurs when 1 mole, once again we're back to 1 mole, of the compound undergoes combustion with oxygen. So now we're in making it do combustion reactions, but it's still referencing this 1 mole, so we'll still see some fractional coefficients when we balance. So for instance, example here, we take that methanol we just formed and we're going to combust it now. So this remains with its 1 here, and then everybody else, the oxygen's the other reactant, the carbon dioxide and water are going to be our products for the combustion. Gets balanced off of this 1 mole of the methanol. So we have the 1 carbon, that's fine. We have the 4 hydrogens, that gets balanced over here. Then you start looking at your oxygens. Always balance oxygen last. So 2 and 1, that's a total of 3. So that's where this 3/2 comes into play in order to balance out the oxygen here. All right, so now it's going to be your turn. You're going to practice real quick doing the combustion of benzene. So go ahead, take a moment, write this out, balance it. Three halves of O2, really, so that would be like, yes, 3 atoms of oxygen. That would be 3 atoms of oxygen. But because oxygen doesn't come as individual atoms, it comes as O2. That's why we fractionally put it as 3/2 of O2. So O doesn't exist in nature, only O2 does. So let's take a look at this one. We're going to go ahead and we have our benzene. So we have C6, oh, I'm going to write it down here instead. C6H6. Our other reactant, of course, is oxygen. And yes, in this particular case, when we're talking about the molar combustion of anything, we're going with CO2 and H2O. Now, if we had an incomplete combustion, you would probably get some carbon monoxide in there, but we're assuming complete combustion and that there is enough available oxygen to make sure everything turns into carbon dioxide and not carbon monoxide. So, looking here, for balancing purposes, do we need to do anything for carbon? Yes. So this is a 6 over here, so we're going to put a 6 here. How about our hydrogen? Yes, this is going to need a 3 here. Once again, waiting till the end to do oxygen. So this is 12, 6 times 2, plus 1 times 3. So my oxygen total ends up being 15 on the product side. So what do I put here in front of my O2? Yes, 15 halves, like so. Exactly right. This is how we would balance our molar heat of combustion for this particular one. Yes, it has to be a fraction. Has to be a fraction. That's how they always write it. They don't put decimals in there. Yeah. So you would never, if you did any kind of research and looked at books or anything on the internet, you'll never see it written as a decimal. It'll always be written as fractional. Good question. Now, of course, solution has its own designation, just like combustion did and formation did. SOLN is for solution. This is when you take like sodium chloride and put it in water and it dissolves. Dissociation, dissolution, all of that falls under forming of a solution here. Molar heat of solution. Now, of course, the reaction describes the molar heat of solution of a compound shows 1 mole of the compound dissolving in water. Now, our main focus is going to be focusing on ionic compounds that dissolve in water. However, this still would apply to, like, if you put ethanol in water or sugar in water, where they are covalent compounds that are polar and would dissolve in water, there would be a slight energy change there when you have their individual IMFs having to separate and then reestablishing those IMFs between the waters and whatever's dissolving. Our main focus and the ones that they usually focus on for AP, though, is when you have ionic compounds dissolving in water, because there's usually a higher amount of energy change in there, and it's measurable in the lab. So we're going to be looking at this from mostly an ionic compound dissolving in water standpoint. So the heat released or the heat absorbed when the substance dissolves in water. And this is the idea behind like cold packs and heat packs. You know, you buy those and then you have to crack them, but then when you do that, you mix the solution stuff together and you end up generating either the heat or either the cold, depending on, you know, which one you purchased and what use you want it for. They usually have the correct kind of salts in there for you to either, if it's a heat pack, generate the heat, or a hand warmer or something like that. Or if you're having a cold pack that, of course, you need, you know, maybe for a sports injury or something, need the cold pack for. That would be like the generalized quick application of this, because a lot of times when the substance dissolves in water, you know, even though we consider it a physical process, because yes, you can do evaporation and restore the original solid crystals, you can separate them physically. However, it falls into the gray area, and people can argue that, oh, it must be also a reaction because you do have heat change in between. You do have bonds breaking, and then the bonds breaking of the ionic compound, and then you have the IMFs of the hydrogen bonds overcoming, and then you have this establishing of those ion dipole forces. And then through all of that some salts end up with a really high heat in terms of they generate a lot of heat from that process and release a lot of energy. And then some salts absorb a lot of heat from that process, and that of course would be the cold pack. And that's the basic idea behind the hand warmer lab, which like I said, I'm going to try to modify down so we can do it. But like for the other two, you have to be able to write reactions for the molar heat of solution. In this case, we're going to specifically look at sodium chloride, which is very easy to do because everybody knows the formula for sodium chloride. And since we're dissolving it, of course, this is going to be denoted as an S here. When it dissolves, it breaks up, of course, into its ions. The sodiums get surrounded by the oxygen sides of the water, and the chlorides get surrounded by the hydrogen sides of the water. And these, of course, then are designated AQ because they are now soluble and are dissolved in the water. That one's very easy to write out. And of course, this is just 1 mole of the formula unit breaking up into its ions. However, something more like ammonium phosphate, a little bit more challenging if you don't have the correct formula written out. So what is ammonium? Who knows ammonium? NH4 plus, right? Definitely have to have the charge on it. It's a polyatomic ion. And phosphate, what's phosphate? Yes, it's PO4 minus 3, exactly right. So now we have this and we can write the correct formula because there's a positive 1 and a negative 3. That means we need 3 of these ammoniums to balance out the 1 phosphate. So we end up going NH4 parenthesis 3 PO4. Of course, this is a solid. It's going to dissolve. Remember on solubility rules, ammonium, alkali metals, nitrates, they're always soluble, so it doesn't matter what it's with. This is going to be soluble. Remember, we're going with 1 mole of it breaking apart into its ions. No, I'm just designating the 1 mole there to remember that this is molar heat of solution, so it's referencing what happens when 1 mole breaks apart and dissolves. So what does the reaction look like over here? For every 1 mole of this, what are we going to get in terms of our ions? How many ammonia ions? When one of these breaks apart, we're going to get 3, good. 3 ammonia ions plus 1 of the phosphate ions. So this would be, it's the basic dissolution reactions you've been writing or dissociation reactions you've been writing when we did solutions. But now we're just referring it to heat. So if the energy amount that's measured by 1 mole changing, that's going to be your delta H of solution. So there's the sodium chloride. Here's the ammonium chloride. Let's talk about delta H of formation. The change in enthalpy that accompanies the formation of 1 mole of the compound from its elements. Okay, so we've already defined that, but it's when they're in their standard states. Now we're going to talk about what standard states mean. When they're in their standard states, these are when these formation amounts have been recorded and put into the tables. Now these tables are found in your textbook in Appendix 2, B in the back of the textbook. So you look for Appendix 2B. The designated pages in the physical textbook are A-5 to A-10. So if you're doing the problem set and they don't give you the table of values, you need to go and look them up on those designated pages in your electronic textbook. Should be able to reference it. They might even have like a quick link that takes you right to that particular section in the problem itself. So when we do some of the problems from the problem set from the textbook, reference Appendix 2B to get your delta H of formations for the different compounds that are in the reaction. Now, standard states, what do that mean? For a compound, we're just talking about the compounds. For a gas, the pressure is exactly 1 atm. That means when 1 atm's reference is atmospheric pressure at sea level, so that's standard pressure. That one's always given for gases. 1 molar, if we're talking standard states of solutions, we're talking that the concentration's at 1 molar. And if we're talking about standard states for liquids or solids, we're assuming they're pure substances. There isn't anything else mixed in there, okay? For elements, we're assuming that they exist in their elemental form, whatever it is, at 1 atmosphere and 25 degrees Celsius. This also applies to the compounds, the 25 degrees Celsius part. And that's why you may have noticed that in the problems, it always references like 298K when you see the delta H with the little degree symbol. The degree symbol is designating that these are the values at standard conditions. And standard conditions are 1 atmosphere and 25 degrees Celsius. Standard conditions are different than standard temperature pressure. The pressure amount does not change. It's still 1 atm. However, temperatures are different. Standard state temperature is 25 degrees. Standard temperature is 0 degrees Celsius. So standard states, think of them as like normal conditions. Like normal conditions is room temperature. Room temperature is about 25 degrees Celsius. Maybe a little bit higher than room temperature, but in the 70s. So keep that in mind. Standard states, like normal conditions. Standard temperature pressure, 1 atmosphere, 0 degrees Celsius, or 273 K. Now, when it says elemental form, that's what we were talking about before. Like all of the nonmetals that are gases at normal conditions, they're going to be gases at normal conditions, like hydrogen, oxygen, fluorine, chlorine, all your noble gases. These ones are all standard state gases at room temperature. Everything else on the periodic table is a solid, except for bromine and mercury, because those at standard conditions are going to be liquids. So don't forget that bromine, mercury, these ones are the weird ones that are always liquids. Everything else besides your noble gases and your normal diatomic gases, those should all be solids on the periodic table. And that's at 25 degrees Celsius and 1 atmosphere. Is when these elements will be in their standard state condition. Now calculating enthalpy change. Here is the more formal, more detailed equation. This one's on your formula sheet. You'll find this one on the formula sheet. Now, of course, this sigma thingy means sum of the molar. This is like from the balanced equation. You multiply it by the moles in the balanced equation times its delta H of formation. And it's basically, you do that for all of the products. You multiply it by its moles, and then you add them all up for the products. And then you do it for the reactant, same thing. Sum of the moles times its formation, the other reactants, moles in the balanced equation times its formation. That's going to end up giving you the reactant part. Remember, it's products minus reactants, and that's going to give you the delta H of reaction. Of course, the little degree symbols designating at standard conditions. You don't have to memorize this one. This is on the formula sheet. And I mean, to be perfectly honest with you, this is a lot to write out before you plug in numbers. So a lot of times what people do, and it seems like AP accepts it, is they just do delta H as like H products minus H reactants. Stick with that, knowing that you are going to multiply it by the moles in the balanced reaction. Remember, the amounts do count here, you know, because this is extensive. So there's 2 moles versus 5 moles. That does make a difference. All right, these elements in their standard states are not included. They are given a value of 0. You won't see them sometimes on the tables because they know, or the inference is you're supposed to know that it's just automatically 0, so it doesn't really factor in. Elements in their standard states aren't being formed. Okay, so these are delta H's of formation. The ones that you're going to see on the charts, those are for compounds. They have been formed from elements. Elements aren't formed. Elements just exist. They just, you know, Big Bang, here they are. They exist. That's how it is. They aren't formed from anything. So compounds are formed from their elements, and that's where they're given that numerical value of the heat change. But when we're talking about just elements in their own elemental states, they are automatically zero. They just exist. They haven't been formed. Consider them the basic building block. All right, exercise 4 is an actual calculation of finding the heat of reaction for sodium plus water, giving you sodium hydroxide and hydrogen gas for this particular reaction. And you'll automatically notice here on the table, sodium and hydrogen are in their elemental states and their heat of formations are zero. However, on the AP exam, they might only give you these two in the middle, and you're supposed to assume zero for the other two. You're supposed to just know that because they're in their elemental states. Now, if we're writing out the, equation here, I'm just going to go ahead and write out the normal one, but, you can take the shortcut that I told you if you want to, because this gets to be very complicated. Look, to have to write all this out, it's kind of a pain. But usually what you're going to want to do for your showing of your work, show the, write out the formula before substituting. So like I said, I'm okay if you just do this, H products minus H reactants, like so. I'm fine with that. This, of course, is the official equation. Now let's go ahead and set up the calculation. Starting with products minus reactants. Okay, so here's our delta H reaction. I use brackets here because I have two products. My first product here, and it has a mole, balanced mole in the equation here, coefficient of 2. So I'm going to multiply that one by 2. So here's sodium hydroxide. It's negative 470. Now technically this is in kilojoules per mole, and this is technically 2 moles. So what you're going to see here is these kind of cancel out. So you're going to end up with just kilojoules at the end. The second product is hydrogen, which is 0. So technically it's 1 times 0, but that's redundant. So you don't even really have to bother writing that in. Minus over here, starting with the reactant sodium. Once again, it's a mole of 2 times 0. That's what it is there, but that's redundant. You don't really have to write that in there. And then 2 times the water. 2 times our water, which is, I guess I should stick with the parenthesis notation. 2 times my water, which is negative 286. And also notice that this physical state of the water happens to be liquid. The number is going to be different if it's different if it's a gaseous form or if it's frozen, that kind of thing. It'll be a different heat amount because there is different amounts depending on the in the bonds themselves and of course with the IMFs. So they are in different based off of their phases. They also have different amounts of energy. When you go ahead and calculate this, now you have to show the equation beforehand. This is important. You have to show this step where you're showing the plugging in. You can go straight to the answer here. That's fine. However, for these problems, it's very easy to get your signs out of whack. And then you get the incorrect answer. I always write out my stuff. So this is like 940. Subtracting over here. What's that? It's like 572 or something. I don't know. I have to recalculate that one. Yeah, it's 572. So this, though, is minusing this negative 572. Okay? So what ultimately happens there, obviously with the double negative, that's going to turn into a plus plus. So here you would do plus plus. So when you finally do your reaction down here, it ends up being like 3 something. 386. So this ends up being 3 the 86 or 368, sorry, 368. I had 68, I just said the wrong number. So this is the ultimate ending for this reaction. Net wise, this is exothermic. It's releasing 368 kilojoules. And I don't know if you've ever, seen sodium go into the water. It kind of like fizzes on the top of the water. So yeah, definitely exothermic. This is the standard plug and chug delta H reaction type question. They're easy, but watch the signs. Be careful with the algebra so you make sure you get your correct signs to get the answer. So there you have it. That's one way they can give you these equations or give you these problems where you have to solve for delta H reaction. They could also do it this way, where you're solving for the formation of one substance. Here we're going to find the formation of the gaseous water. This is missing on the chart. We don't know this value. We know the delta H of reaction. We know the other three. Well, now our formation of our water becomes our variable. So it's kind of like the working backwards type of the problem. So once again, write out your generalized equation here, like so, and then we start plugging and chugging. So my delta H here is negative 902.0. Over here, I'm going to start with my products. 4NO, there's 4 of them, so 4 times NO, which is the positive 91.3. Plus my other one, this is what I'm missing, but there's 6 of them, so don't forget to multiply it by 6. And I'm going to designate this value as X. I'm going to put that as X, because that's what I'm missing. Then I subtract out my reactants. First reactant is ammonia. 4 times my ammonia, which is negative 45.9. Plus, oh wait, that's elemental oxygen, which is 0, so I really don't have to incorporate that in. I can just leave that part out. Now I have to do the algebra math and find out what X is. So 4 times the 91.3. This is what, 365.2. This is 6X minus 4 times 45.9. Now remember, it's a minus here. So this ends up being plus plus. Okay, and all of this equals the negative 902.0. These two combine like terms. I know the algebra seems probably pretty easy for you. So this is 548.8 plus the 6X, and that gives me this. Okay, then, move this over to the other side. And we end up with negative 1450.8. That equals 6X. Divide by 6. And you're going to get negative 241.8 kilojoules per mole. Remember these formation values are in kilojoules per mole. That's going to be for the water. Technically, all you have to write on your paper is this part, and your answer. But if you can't mentally keep control of those signs and everything, I would, keep working it out. Just a suggestion. But you know your own ability and how you can keep track of things, so do what, feels right. All right, what must happen for a reaction to occur? Reactants must collide. Must collide with the correct orientation, and they must collide with enough energy, the activation energy. So the atoms in the reactants are going to rearrange, okay? And so what else has to happen? We're going to be looking at bond energies and bond breaking and bond forming in just a little bit, but I'd like to review collision theory just mildly and how to, speed up chemical reactions and the different features of how that takes place. So I have this short TED Ed video for you to watch. That should get us to the end of the class for today, and then we will start with the bond energies next class.